Hey guys, Miss Marusik here, and in this video we're going to talk about calculating with Gibbs free energy and using it to determine the thermodynamic favorability of a particular process. Now, as a reminder from our previous video, we looked at the idea that a thermodynamically favorable process would have an increase in the entropy of the universe. The problem is that the calculation that we did only determines the entropy change of the system, the actual reaction. It doesn't determine what's going on with the surroundings. And so, unfortunately, what's going on with the surroundings is really hard to measure as far as the entropy change. And so we're going to instead need to look at a balance of both entropy and enthalpy to determine thermodynamic favorability instead. And the way we're going to do that is by utilizing what is called Gibbs free energy, which is defined as the amount of energy in a reaction that can be used for work. And what we want to do is we want to look at the Gibbs free energy change for a process, and by looking at that change we can determine if a process was indeed thermodynamically favorable. Now, we're going to be calculating that change at SATP conditions. So you notice back here, our delta G has that little degree symbol with it to indicate that we're working with 298 Kelvin and 1 atmosphere of pressure. And so what we're going to do is we're going to calculate that change, and based on the sign that we see, we'll know if our overall process was thermodynamically favorable or not. Now, there's two calculations that we're going to look at in this video, but there are actually several calculations we can use to determine delta G. The two that we're going to look at is, first off, the equation that looks very similar to what we've done with enthalpy and entropy, where the Gibbs energy change is equal to the change in Gibbs energy of formation of all of the products minus the Gibbs free energy change of forming all of the reactants. So again, a products minus reactants scenario, and again, we're going to have to take the coefficients into account. The other equation that's really commonly used is this one down here, where the Gibbs free energy change is equal to the enthalpy change for the reaction minus our temperature multiplied by the entropy change of the reaction. And so we're going to see how to work with both of these in this particular video. However, a couple quick things. First off, when you're doing the delta H minus T delta S, most of the time we are using SATP conditions, and so we would assume 298 Kelvin unless otherwise stated. Now, the other thing we have to be really careful with, which I mentioned in our previous video, is that delta S is often in the terms of joules, but delta H and delta G, our enthalpy and our Gibbs energy, are often given using kilojoules. And so you've got to do a conversion to make sure those units match up, or you're going to get your answer wrong. So just be very careful with those units. But the way that it works once I calculate my delta G is that if the delta G value is greater than 0, meaning it's positive, what that means is that overall our reaction, our process, has had to take in some amount of work. We have had to provide some energy in order to get it to occur. So therefore, the reaction is not thermodynamically favored. It is not spontaneous as it is because the reaction doesn't occur on its own. Now, if the delta G is on the nose at 0, then the reaction would be at equilibrium. However, if the delta G is less than 0, meaning it's negative, then that means the reaction is thermodynamically favored to occur because now it's releasing work elsewhere. It's not taking it in. It's actually able to provide work to other places. And it's going to occur without any external intervention. Now, you notice I kind of starred and bracketed this little statement here because the key thing I want you to remember is that if delta G is negative, then it is thermodynamically favored. It is spontaneous at those sets of conditions. Now, what I want to do is I want to kind of talk through our delta G equals delta H minus T delta S to think about what kind of enthalpy and entropy conditions would we need to ensure that delta G comes out negative. If this is the goal to get us to be thermodynamically favored, what signs do we need on delta H and delta S? So let's talk about that using this chart down here. Now, I put a funny meme down here, but actually it's really helpful to remember our ideal conditions. Chemistry is the one time it is favorable to be a hot mess, meaning hot, we want exothermic reactions that would release heat and feel hot to the touch. And messy, we want things with lots of microstates and lots of arrangements, and so therefore we want a positive delta S. We want to get more messy. And so you notice here that when delta H is negative and when delta S is positive, that this is the ideal set of conditions. Why? Because it's always going to get us a negative delta G value. Let's talk about why. Think about your equation down here, okay? If I have a delta H that's negative and I subtract with a delta S that's positive, and remember the T value, if I'm using Kelvin, I wouldn't have any negative value, so that's always going to be positive. I should always be having a negative minus a positive. So it doesn't matter what value I put in for T, you're always going to get a negative delta G value overall. So what that means is that when we are exothermic, and you notice I put a little happy face because that's a good condition to have, and whenever I have increase in entropy, so I put another little happy face, that when both of those are happy faces, that delta G is always negative at all temperatures. And that would mean no matter what, our reaction would always be thermodynamically favorable. Now, let's talk about changing up those conditions. Let's say that we keep that delta S as positive, so we have an increasing entropy, but I see a positive delta H, which is not ideal, so I put a little frown. When I have one that's a frown and one that's a smile, then that means there's a chance it could be negative for the delta G. I need to think about my numbers. So to come down here and let's think about our numbers for a minute. If delta H is positive, and then I'm subtracting a delta S that's also positive. If I want delta G to come out negative to be thermodynamically favorable, then I need to be subtracting a really big term over here. And to be subtracting a really big term, that would mean that I want this T value to be large. If that temperature value is large enough, then I'm going to subtract a term over here that's larger than whatever this delta H was positive, and so that would give me overall a negative delta G, which is what I want to be thermodynamically favorable. So therefore, for this one, we would say that it is thermodynamically favorable at high temperatures. If I have this combination, I want that temperature to be high in order to ensure thermodynamic favorability. What that also means is that this reaction is driven by entropy. The entropy is what's providing the opportunity for this to be thermodynamically favorable, because the enthalpy is not acting in our favor here. Now, let's say we switch it up again. Let's say now I have my delta H negative. I'm exothermic, which as we know is favorable, so I put a little smiley face. And I put a delta S though of being negative, meaning I'm getting less entropy. I'm going to less microstates. Now, we know that's not ideal, but the entropy gives it a chance of possibly being thermodynamically favorable. So again, I'm going to think through my math here. Okay, if my delta H is negative and I am subtracting the delta S being negative, which subtracting a negative would end up making that whole term positive, I need to make sure that this negative delta H term is larger than whatever this minus T delta S term is. Because if this minus T delta S is too big, then that's going to throw the delta G positive. So I need this term over here to be fairly small, which means I need the temperature itself to be small in order to ensure a negative delta G value, in order to ensure thermodynamic favorability. So you notice I put on here, this is only thermodynamically favorable at low temperatures, and we would say that it is driven by the enthalpy. The enthalpy is what's providing us with the possibility of us actually being thermodynamically favorable and getting a negative delta G. Okay. Now we got one more combination. Let's say our delta H is positive. This is endothermic. Well, we know that's not good. And entropy is also negative. We're going to less microstates. We also know that that's not good. Let's think about our math for a second. So over here, what would happen is that our delta G would always end up positive. Why? Because I would have a delta H that's positive minus a delta S that's negative, which those two terms would end up creating a positive. And so it is impossible here to get a negative delta G. So therefore here the delta G is always positive at all temperatures with this combination, and it is never thermodynamically favorable. All right, with that said, let's go ahead and start to see how these calculations would work on the next page. All right, now there's two last statements up here before we jump into a calculation. First off, it says for spontaneous reactions to have a negative delta G value. As a reminder, if the delta H is negative, then that means our reaction is thermodynamically driven by enthalpy. The enthalpy is providing that opportunity for us to be favorable because, again, it is ideal to become more energetically stable. It is ideal to go to a lower energy throughout our process rather than to get to a higher one. If the delta S is positive, the reaction is thermodynamically driven by entropy. The entropy is providing the opportunity for us to be favorable because it's ideal to create more microstates. Now, a reaction can be driven by both if the delta H is negative and the delta S is positive. If we have that ideal set of conditions where we're exothermic and increasing entropy, then it's driven by both, which is why it is the best type of reaction that we can have, because both enthalpy and entropy are driving us toward thermodynamic favorability. Now, I want to re-emphasize the fact that just because a reaction is favorable, just because it's spontaneous, does not necessarily mean it happens quickly. It can still be very, very slow, even though it is spontaneous. Now, it says here, if a process is known to be thermodynamically favored, yet does not occur at a measurable rate, we would say that that reaction is under kinetic control, that the kinetics of the process are preventing us from seeing a measurable reaction taking place. And we're going to see an example of that here in just a little bit. This also likely means that we have a really large activation energy that's preventing us from seeing a fast reaction. Remember, the bigger activation energy gets, the slower that reaction will take place. All right, let's go ahead now and jump into those calculations. So first off, it gives us a balanced reaction here to answer the next few questions, as well as some data in a chart over here. So the first thing they want us to do is using the information in the table to find the delta H of a reaction. And we notice they give us all the heats of formation of both our reactants and our products. And so this is a throwback here to Unit 6, where to figure out the heat of the reaction, we do the heat of formation sum of all of the products minus the heat of formation sum of all of the reactants. Now here, our only product was the AlCl3. There were 2 moles of that, so I multiplied that by the heat of formation, which was a negative 704, minus the reactants. However, you notice the reactants had heat of formations of 0. Now think about why for a second. Do you remember what would cause the heat of formation of 0? That's right, we've got elements in their standard state, right? And so they had that heat of formation of 0. So here, once I do that math, that gets a negative 1408. I see this was in kilojoules per mole of the substance, so that means I end up in kilojoules per mole of the reaction. So this is exothermic, which is good. We like to see exothermic processes for thermodynamic favorability, right? That's a good thing. Okay, let's now do the entropy. So here it wants us to find the entropy of the reaction. So again, I'm going to do the sum of the entropy values of all the products minus the sum of the entropy value of all the reactants. But again, these entropy values over here are in terms of moles of the substance, and so I need to address the coefficients in my calculation. So my product here was the AlCl3. There were 2 moles, and I multiply that by the 111 for the entropy value, minus the sum of all the reactants together. First reactant was the aluminum. There were 2 moles of that at a value of 28. And then we have our other reactant, which was the Cl2. I had 3 moles of that at a value of 223. So putting all that in my calculator, that gets a value of a negative 503. Now be careful with your unit up here. I notice that's in terms of joules per Kelvin times mole of the substance. So I'm going to end up in joules per Kelvin times mole of the reaction. Now, I notice that that's negative. I know that that's not super ideal. Like, I'd rather see a positive entropy value, but this is only for the system. It doesn't take into account what all the surroundings and the whole entire universe is doing. And so because at least one of these things is in a good set of conditions to maybe get thermodynamic favorability, I'm going to have to calculate here to see if in fact we are thermodynamically favorable or not. And so that's where the third step comes in. They want us to find the delta G of the reaction with the information that we have already done. So since I had my enthalpy and I had my entropy, I'm going to plug those in to my delta H minus T delta S equation. Now, I do have to be careful of a couple things. First off, they don't give me a temperature value here, but they use a little degree sign, and so I'm going to assume we're at SATP conditions, so I assume that my temperature is 298 Kelvin. However, remember, this delta H was in terms of kilojoules, but this delta S was in terms of joules. So notice when I plugged in my entropy here, I did move my decimal point over appropriately to get the joules into kilojoules. Once I get those units to all match up and I get my temperature plugged in, now I just plug into my calculator. And when I plug in all of that math, I get a value of a negative 1258, and that would be in terms of kilojoules per mole of the reaction. And the unit of Kelvin would have canceled out right here. Okay, so I would say, hey, that's negative. That's thermodynamically favorable. So honestly, kind of skipping ahead down here just a little bit, it says here on part D, is this reaction thermodynamically favorable at standard conditions? And I would say, yes, it is favorable, as the delta G was negative. Also, I can go ahead and answer E down here. It says, which of the following statements is true regarding the reaction above? Well, as we said, the enthalpy, the heat, was in a favorable condition. It was negative. It was exothermic. But the entropy was also negative, but I want that to be positive to be favorable. And so this reaction was really driven by the enthalpy value. The enthalpy being exothermic was the reason why we even had a chance of being thermodynamically favorable. If it was up to the entropy, this would not have been favorable. Okay. Now, they give us another kind of set of data here that we can also use to find delta G. You notice here they give us the delta G of the formation of all of these substances. And so in giving us that data, we could do the delta G of the reaction equals the sum of the delta G of all the products minus the sum of the delta G of all the reactants. And when I plug in that data, and again, I see my two reactants here are 0, that too gets a value of negative 1258 kilojoules per mole of the reaction. So I know I got to the same answer here, but that proves the point that depending on what kind of data you're given, you should still be able to get to the same overall answer, regardless if you're using enthalpy and entropy to calculate it, or if you're using the Gibbs free energy of the formations of those substances. Now, one last thing I'm going to point out on this one, it says, what do you notice about the Gibbs free energy formation values for the elements in their SATP state? So looking up here, again, those elements that were in their standard state had a Gibbs free energy formation value of 0. So just like we saw with heats of formation, elements in their standard state should have a Gibbs free energy formation value of 0 as well. So something kind of interesting to point out there. All right, let's go ahead and look at a few more calculations on the next page. So on this next question here, it says, hey, for ammonia, NH3, the standard enthalpy of fusion value is 5.65 kilojoules per mole, and the standard entropy of fusion is 28.9 joules per Kelvin times mole. So it asks, will solid ammonia spontaneously melt at 200 Kelvin? So first off, I'm like, well, they gave me some delta H value and a delta S value. So I'm probably going to be using that delta G value equaling delta H minus T delta S. And so I'm going to plug in all of my pieces into that equation. Now here, couple quick things. First off, they mentioned that we are melting. So remember with enthalpy of fusion, they don't naturally give us a sign there. We have to decide a sign. But if I'm melting, I'm putting heat into that. So I'm putting in heat, I should be having a positive value for that. Now, our temperature here is no longer 298. This time I'm dealing with 200 Kelvin. And so you notice when I wrote my formula here, I didn't put the little degree symbols with the delta G because I'm no longer at standard ambient temperature and pressure conditions. So I have to be careful there. This is not at standard temperature of 298 Kelvin. Now, the last piece here is my delta S, but I have to be very careful on the units of that delta S. This was in joules, but that doesn't match up with my enthalpy of fusion here, so I did have to convert this into kilojoules. And so I went ahead then and just plugged everything into my calculator, and that got me a value of a negative 0.130 kilojoules per mole. And this is of a phase change, but it works just the same way as I did for a reaction. This being a negative value here for delta G, that means this process was thermodynamically favorable. That ammonia will melt at 200 Kelvin. Now, our next question here says, what is the approximate melting point of ammonia? So it wants to know, where do we go from this being unfavorable to all of a sudden it being favorable? Where do we make that transition at? And if you really think about where we make that transition, we make it when delta G goes from being positive to negative, right? When we transition over that sign, when delta G is equal to 0, that would be the break point of when we are considered favorable and not. So I'm looking for the point where that phase change occurs, meaning I'm looking where that equilibrium occurs between liquid and solid. And so I'm looking for where that delta G equals 0. So once I make that determination, then I just plug in my data from up above. So again, my delta H is a positive 5.65 minus my temperature, which is my unknown here. Now, you could leave it as T. I went ahead and plugged in X. I know for some of y'all, you like solving algebra better when you see X. And then I plugged in my delta S value, again, that converted value just like I used right up here. And when I did that, I got that X equals a 196 Kelvin. Now let's think about that for a minute. What that means is that anything above 196 Kelvin would melt. Which makes sense because we just said up here 200 Kelvin would melt, right? So that's above 196. But anything below 196 would end up throwing this delta G to be positive, and so would no longer be favorable. So this was my breakpoint between being favorable and unfavorable. Any temperatures lower than 196, that melting process would no longer be spontaneous. It would no longer be thermodynamically favorable to occur. All right, let's look at the next one. This one is kind of interesting for a couple different reasons. The first one is the fact that they give us some individual reactions here where they give us a delta G value. Now, I know we didn't see this as one of our equations listed out, but if you think back to Unit 6, we learned a process called Hess's law, which basically the way it worked is that if I had reactions that I could manipulate around, I could use those reactions to figure out the heat change for an overall process. We can do that same exact thing when dealing with Gibbs energy calculations. So with that said, what we want to do here is calculate the Gibbs energy change for carbon as a diamond to change into carbon graphite. And so they gave us equations up here that had diamond and graphite involved, and they gave us those delta G values. However, the diamond is on the correct side of the equation to where I want it, and so I just rewrote that equation here with the delta G value. But I noticed that the second equation, the graphite, is on the wrong side. Now, it does have the correct coefficient in front of it, but I'm going to need to flip that equation around. And remember, when I flipped heat values, I changed the sign on it. Well, we're going to do the same thing with the delta G value because, again, it's just an energy amount. So in flipping that equation around, that would end up flipping the sign on the delta G. Now look what happens here. You end up with CO2 on either side, that would cancel. You end up with O2 on either side of the arrow, that would cancel. And so the overall equation that would leave you with would be the carbon diamond changing into carbon graphite. And so then once I get these manipulated in the correct way, then I just simply add up my values. And when I do so, I get here a delta G of the reaction being a -3 kilojoules. And you could put kilojoules per mole of the reaction if you wanted to. Sometimes we see that designation shown and sometimes we don't. So since here they just gave us kilojoules, if you wanted to leave it as just kilojoules, you could totally do that. But I want to point something out. That's a negative value. What that means is that this is thermodynamically favorable. That means spontaneously, on its own, without any help, diamond will turn into graphite. And I know some of you are thinking, wait a minute, Marusik, does that mean like diamond jewelry, like my ring that's a diamond, will just spontaneously turn into graphite? Yeah, it will, if you wait long enough for it. Here's the key. This reaction is incredibly slow. So slow that you'd be sitting here waiting a couple million years for your diamond to go turn back into graphite. Now, I don't know about y'all, but I don't plan on being around here when that happens, okay? So what happens is that this reaction is very slow. It does not occur at any measurable, visible amount. And so what that means is that this reaction is under kinetic control. While it is spontaneous, while it is thermodynamically favorable, the kinetics are preventing it from being visualized in any measurable amount. Now, what could you do to speed up this reaction? Well, as with any reaction, you could add a catalyst to it. But what that would do is it wouldn't affect anything on the delta G. That delta G of the reaction is still -3 kilojoules, is still thermodynamically favored. The only thing I would be doing to it is speeding up the kinetics of it. So we have to be very careful. Are we talking about thermodynamic favorability and spontaneity? Or are we talking about speed? Because those two things are very, very different. All right, one last thing down here. Let's talk about coupled reactions, which actually uses that Hess's law idea that we saw up above. It says that we can couple an unfavorable reaction with a favorable one in order to make the overall process favorable. Now, to do this, you have to have two reactions that have a common intermediate because I would need things to cancel out when I'm doing my Hess's law calculation. So, let's look at this here. I have Fe2O3 making 2Fe plus 3/2 O2. And they give us a delta G value for it. Now notice that doesn't have a negative in front of it, meaning that this is a positive delta G, which means that this reaction as is not favorable. But let's say I want to force it to happen. And so to do that, I would need to pair it with a second reaction that would cause the overall process to be favorable, so that way this reaction could take place. It's kind of like I'm needing to force this to occur, so I'm going to couple something with it that'll help to force this to happen. So that's where this second equation comes into play. We have CO plus 1/2 O2 yielding CO2, and they give us a delta G value for this process. Now, I want to get to this overall equation that we see down here. Okay. Now I notice that the Fe2O3 is on the correct side of the equation for where I want it. And I also notice it has the correct coefficient in front of it. So what that means is that that half reaction is good as is, and I just rewrote it with its delta G value here. However, my other reaction, if I look at the CO and the CO2, while they're on the correct side, they don't have the correct coefficient in front of it. And so this half reaction has to be multiplied by 3. And when I do so, that delta G value will also get multiplied by 3. And so what happens here is that this 3/2 O2 would cancel out on either side of the equation, so I don't end up with it in this overall equation. By the way, that 3/2 O2, that is the common intermediate that both of these reactions would have. to have a coupling situation, you have to have that common intermediate so that things can cancel out and give you your overall equation here. Now, once I get those delta G values, I just simply add them up together, and that gets a value of a negative 108.3 kilojoules, which is favorable because it has a negative delta G value. Now, that means we had something that was unfavorable, but now because I put it with something that was super favorable, this overall process ends up favorable, and so now this reaction is being forced to occur because the other one is forcing it to happen. So that's kind of the idea behind coupling reactions, is that we couple a favorable one with an unfavorable one to help that unfavorable reaction actually take place. All right, I hope you're feeling good about calculating with Gibbs free energy and determining if a reaction is thermodynamically favorable, spontaneous, or not. And as a reminder, all you're looking for there on spontaneity, on thermodynamic favorability, is a negative delta G value. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.